Okay, so what we're going to look at is probably over the next week is just looking at each sort of sub-chapter, nearly a lesson as a sub-chapter, try and get through it. Okay, got a fair bit to get through. So we're up to 6E, which is the shortest distance from a point to a line. All I'm going to do is just go through a couple of examples quickly, and they're examples that are in the book. The reason is that it's probably a fairly specific sort of question. Looking at other textbooks, there aren't really any questions directly like that as such. The textbook does initially just use a two-dimensional type vector and two-dimensional idea, and it's probably easier to visualize a situation where that's the case, but certainly when it comes to the test or exam, you could just do the same thing in 3 dimensions. So an example of where you might want to use something like this, where you're looking at a point and trying to work out the shortest point or the shortest distance from that point to a particular line or something along that, is the example that they start with, which is a ship that's sailing along a straight line from A to R, okay, and continuing along that line. And we have a point P, which is a port on the coastline. So really what it's looking at is saying, well, what is the shortest distance that we can travel from P out to that line, or, where do we go along that line before we turn in, okay? The main part, if I get this pen to work, let's cut it. So we're looking at the line that sort of goes out there. The important part is that it's going to be 90 degrees where it hits the line. That's the key. So the key to all of this is using this, which is the dot product, saying that the dot product between two vectors, if that equals 0, then you've got a perpendicular or a 90 degree angle between the two vectors. So we're just using that, just an application of using that, nothing more than that at this stage. So their first example is just a two-dimensional vector given a vector equation. What's the shortest distance from a point to that line? Okay. Well, what we're going to need to do is think, well, I've got a line, so I'll just draw a random line in. So that's my line. And I've got a point somewhere over here, which is 5 minus 1. And I want to be able to go across from this line over to here to make a 90 degree. But that effectively means I need a vector here as well as the lines vector. Okay, so I've got a vector equation. It's very easy to get the direction vector for that line. Okay, remember our direction vector comes from this part here, so this is our direction vector. All right, so we might just use B. So B is just equal to 3 minus 1. But our other vector goes from P to this point of contact. I'll just call it A, doesn't matter. But it goes from P to A or from A to P. It doesn't actually matter for this question. But what we want to do is find out what that vector would be. We don't have an actual point A in this question. All right, what we want to know is just what the distance is. So we need to write a vector, but it's going to have to be in terms of t. So we've got from P to A. A is our unknown. So we've got a point. What have we got here? We know that the point is going to be at A. It's going to be equal to 1 plus 3t, and 2 take t. Okay, that's the point A. We just don't know what t is for that. And we know that P has the point 5 minus 1. So therefore, the vector AP is equal to 5 minus 1 plus 3t, and minus 1 minus 2 take t. Alright, so that's going to be what? 5 minus 1 is 4 plus 3t, and minus 1 minus another 2 is minus 3, plus, that should have been t, this other one should have been minus, shouldn't it? Okay, so we've got now two vectors. Yes, there's a parameter t involved in it, but there are two vectors. So if we did, if we go back to the top and remind ourselves that what we want is this part here, okay, it's P to R. I should have used the same letters. I've just used different letters, doesn't matter. So we're doing the dot product, okay, so the dot product of minus 4 minus 3t minus 3 plus t, and our b is 3 minus 1, okay, that has to equal 0. So therefore, we've got 3 lots of minus 4 minus 3t, and I'm having a mental blank. What are we doing for dot product? Adding them. So minus 1 minus 3 plus t equals 0. So minus 12 minus 9t plus 3 take t. So we've got minus 12, we've got plus 3 is minus 9, minus 9t minus that is minus 10t equals 0. Minus 9 minus 10, I've just done that one. Minus 10t equals 9, t equals negative 9 over 10. Okay? Has someone got that example open? Is that the right t?
15 over 10.
15, which wherever I made my mistake. 3, it should have been.
No, he's doing example.
Oh, no, you're example 10. Yeah, sorry.
No, it's not example 10. No, this is the previous one.
Example 9.
Should have 15, should have it. So that looks at 12 and 3 minus 3 minus 1 minus 3 makes 3.
They do at the very start, they just, so the dot product is minus 3. Yeah, no, it's not three. They have 3 minus t, positive 3 minus t.
Positive 3 minus t. Minus 3t, 4 minus 5. Hang on, here's my, I've got here AP. I've written a negative, an extra negative in here. Yeah, I've got an extra negative there, which hopefully will fix that up, because that becomes, yeah, that becomes 12, which gives this to be 15. That's what we want. Yep. 15. And therefore, so the answer was what?
15 over 10.
Which is 3 on 2.
3 on 2. Yep, 15 over 10. Yep, that's, yep. Good. So 15 on 10, which is equal to 3 on 2. Okay. So that doesn't give us, the question itself says, what is the shortest distance? That gives us the parameter t, which allows us to find the point, okay, that I've labelled as A. So we're going to find the point using that. All right. I'm not going to put it in. You can put in.
Or would you just find the vector and
Yes, well, yeah, but you'll need to put t in to be able to find that vector. Yeah, the first thing you'll have to do is find. That's right. You can find the vector. So in fact, you're right. You could do it here as well. Do it at that point. Plug it in, and you've got the vector. Or down here would be even better.
Yeah.
And once you've got that vector, then you can find its length. Yeah. Okay. So the textbook's got the example there. You can follow with it, but that's the process. You need to find that parameter t. I'm not going to do example 10 because it's there, but just to very quickly go through it, what we're saying is that we've got a ship that's moving sort of out from point A, and it's got a direction vector of 3, 4. It's got a speed that it's moving at. It says write an expression for the position of the ship. Okay, so the position of the ship is very similar to we're trying to get like a set of points. All right, and it wants for the number of hours after leaving the port. So it's 10 kilometers per hour. All right, so the first step is to find the length of the direction vector as like a unit of 1. So since the speed is 10, once you've got the length there, you can plug that in and say, well, it does 10, so it's done 5 kilometers within that. So what we're doing here is hours. It's in hours. So we get our 10 kilometers an hour. Okay, 1 unit would be for 5. So we get our vector that's useful. Why do we want that? Because we're going to say, okay, there must be a point that we can use. All right, we've got the -8, 3 as the starting point A, and we've got a direction vector of 6, 8. Okay, with t, the reason that we've changed it to 6, 8 and not left it as 3, 4 is because that way we've got it in hours. Okay, because what it's saying is in 1 hour, it can move 10 kilometers. 1 unit on there is only 5 kilometers, so it's been changed to make it so t is in hours. All right, that's the purpose of this. Oops, that's not what I want to do. That's the purpose of this step here. Okay, a unit of that vector would only be 5 units long. Okay, but we know in 1 hour it should go 10 kilometers. So we change that to being a vector of 6, 8 rather than 3, 4. That's the purpose of that. And then you can use that, just like in the previous example, to get a set of coordinates. All right. And the t then is in hours. That's the important part. That's the first part in A. Okay. And then find the time when it's the closest. Same process as before. Find the vectors, do the dot product. Okay, and you can see it's very much a same steps as the previous question. Okay. The last one, and there isn't really that many questions in the book that look at 3 dimensions, but we can do all of this stuff in 3 dimensions. But one of the things that it asks for is finding the coordinates of the foot of the perpendicular. So basically, it's what is the actual point where if you drew your line in, you get a nice a perpendicular from the point which has been given to the line that's also been given. Okay, so I'm not going to go through all the steps, but let's just draw a quick diagram. We've got a line, okay, that has parametric equations as given. Therefore, the direction vector of that line must be 2, 3, 1. Okay, we've got a point somewhere that is -1, 2, 3. Okay, and from that point, if we drew a line here, made that 90 degrees. So this point is point P. Doesn't give us a thing. I'm just going to call this point A. Okay, so point A is what we're trying to find out in the first part. All right. So once again, we have a point A in terms of t. Okay, so point A is going to be equal to 1 plus 2t minus 4 plus 3t and 3 plus t. That's the point. Okay, so just like in the first example, you can use AP, the vector AP, to be able to work out the point of A. Okay, sorry, you can use that to work out the vector AP. Then you can do the dot product and work backwards and get to the t value. Then you plug the t value back in to your coordinates of A. That'll give you your coordinates. Okay. Once you have the coordinates of A, and you have the vector AP, you can work out the shortest distance to the line. Okay, so very much like the first example, but you have 3 dimensions to work with. That's the only difference. Okay.